I've taken a sinusoid, I've sampled it at a fixed rate. You can see I've sampled it at some high. I've taken 1,000 points over here between the times, and then I've sampled at some additional rate. So I've sampled that smooth signal more widely. And here is where those dots are. And the big reveal for this is that that's the original sinusoid that those dots came from. And so those of you who weren't in yesterday's lecture may find that surprising, but the reality is there are an infinite number of sinusoids that go through those exact same dots. I can just keep increasing the frequency and like they'll kind of match up. And it's actually quite fun to play with the slider. So to kind of see the patterns that the sampled signals make. Sometimes they appear to kind of resemble kind of multiple sinusoids. So if you look over here, you know, there's these patterns that emerge on that sample. So I'm taking exactly the same signal here, and I'm just sampling it at some varied rate. And you can see there seems to be almost like, I think it is clearer, that seems to be kind of like two sinusoids weaving in between one another. Now, I say seems to be because what your eye is doing is kind of connecting the curves or connecting the dots. And really what we're telling each other is that if we really want to be able to sample or reproduce a particular sinusoid, the rule is that if I need at least 3 dots on a full period of the sinusoid. Actually, like it's posed with a less than, not a less than or equal. So I need a little bit more. That middle dot there actually can't be 100% in the middle. It has to be a little bit like closer than that. And if it's just a little bit closer than that, I can uniquely put a sinusoid through those points, as long as I have the second requirement, which is that the sender guarantees that there were no higher frequency sinusoids in the signal when they sampled. And what's important to understand is that once I receive these sampled signals, in other words, if I have received a file containing the numbers that somebody wrote down or that a device sampled from that signal, the high frequency content and the low frequency content for those particular frequencies alias each other. What that means is they look like one another, and this is kind of the lesson of this thing is that you can kind of get different looking sinusoids, but if you play this the other way, it means that those high frequency sinusoids will just add up with the low frequency sinusoids. And when you actually try to reproduce the signal, because of that first thing that I said, or the second requirement that I said, which is that you guarantee that there were no high frequency sinusoids, I can't disentangle them. And so I'll just play back that high frequency sinusoid as though it were a low frequency sinusoid. And what that means is that high frequency content actually messes up your low frequency content. So that's an important thing to understand, that we have to guarantee these two things when we sample. We have to know what frequency range we're interested in, and we have to know that up front. We cannot delay that decision until after we have sampled, because if we have sampled at an insufficient rate, we have irrevocably lost the high frequency information. There's no way to get it back. Why is that the case? Because of this aliasing phenomenon, where the high frequency content will appear to be low frequency content. And so there's no way for us to guess which one of those extra sinusoids there were, because it will fundamentally be attributed to that low frequency content. So I need to understand the signal that I'm trying to sample first, and then I have to process that signal up front. I have to filter that signal. And let's say that there's a kind of lots of different interesting frequencies, but most real signals tend to go down towards the high frequency region. In other words, most real signals don't have really, really high frequency content. When you're talking about stuff like wires, for instance, wires at very high frequencies become effectively inductors or capacitors, and so they tend not to be able to propagate signals at high frequency either. So the actual wire itself has a frequency response, and so the wire itself will actually remove some of those frequency responses. So it's really, really hard to transmit super high frequency. And so what we'll do is we will decide, and one of the ways that we will decide this, one of the common ways that we think about, like when we think about, for instance, audio signals, is we know that humans cannot hear certain frequencies. So most normal humans, humans like you, can probably hear up to about 20,000 kilohertz. Humans like me can probably hear up to maybe about 17. I'm getting older, so my ears aren't what they used to be. But every human has some high frequency cutoff at which you no longer perceive audio sounds. And so it's useless to reproduce those sounds when we're playing back audio for somebody to listen to. And so we choose some cutoff, and according to the Nyquist sampling theorem, we say if I want to reproduce signals up to, in this case, something like 22 kilohertz, then I need to sample at a rate of 44 kilohertz, which is the sampling rate of most kind of, well, it's the sampling rate of CDs, basically. And a lot of audio is sampled at 44 kilohertz. If you're into audio production, you may know that like some of the really high accuracy stuff is sampled at 192 kilohertz. And that is actually in order to allow for noise artifacts not to affect the low frequency stuff. So it's not really worth it to listen to those high frequency or to those highly sampled signals. Probably your actual audio equipment can't actually reproduce those frequencies anyway. Now, what do? We take that audio signal, and before we sample it, and I'm just going to introduce a little bit of graphical terminology here, we represent this idea of sampling a signal with a very kind of old school way. So that's the same, you may be familiar with the icon, like the circuit diagram symbol for a switch. That's the circuit diagram for a switch. And so we draw these things. Sometimes people put in a little arrow, and sometimes people put in the sampling rate at the bottom. It depends on kind of how these things work. Also, there doesn't seem to be like a really common direction for that switch to go into. I find myself always drawing it so that it looks like Pac-Man eating the incoming signal, but that's just me. It doesn't really matter. Now, what happens in between the actual recording and the sampling is that we have this filter, and the best filter, you'll see people talking about what is called a brick wall filter. And I want you to understand that I'm going to start drawing these diagrams now of the frequency response of things. So, and you'll see that most of the time I'll be drawing only the gain part of the filter, because that's usually kind of just an idea of like what kinds of signals get through. The phase part is important, but it's kind of less important to understand the behavior of the filter than the gain part. And so the best kind of filter for this is that if I want to reproduce up to 22 kilohertz, then I have to filter out all the frequencies, because remember, I'm going to sample at 44. Why? Because I want to have those 3 sampling points in the sinusoid. And just also a little bit of a note, you'll see that there is a little bit of there are 2 ways of referring to frequency. You may be familiar with radians per second, which is the way that like pops out of the math. So when we're talking about omega, if we say that some kind of frequency response is g I omega, if we write it that way, this omega has units of radians per second. But you'll also very commonly hear people talking about frequencies in hertz. And hertz is periods per second. Okay? And so a period of this big sinusoid over here is that whole time, right? And so when we talk about hertz, we're actually talking about periods per second. And that is one period, and that is like the time frame over here. If this is 0 and this is 10, then that would be a 1/10 hertz signal. Does that make sense? Now the relationship is clear. To go from periods to radians, you just multiply by 2 pi, right? Because 1 revolution is 2 pi, and so there are 2 pi radians in a revolution, and a revolution is a period, okay? So just be familiar with those terms. While I'm talking about nomenclature like this, a very other important thing is you'll see that there's this thing called the amplitude ratio. The amplitude ratio is effectively what we plot on the, what I will commonly call the gain part of a Bode diagram, but which is more commonly, or which is more correctly called the amplitude ratio. You will also see that these things are commonly reported in two different sets of units. Either they are simply reported as is, as the amplitude ratio, but you'll also see people talking about decibels, especially when you're thinking about audio. You all have seen probably somebody talking about the sound in decibels. And decibels is something that is quite similar if you remember the way that pH is defined. It's also a similar kind of scale comparison. So basically decibels, so to get the decibels of something, it's 20 times the log base 10 of that thing. And so if something's 20 decibels, right, that means it was originally 10 by itself. Now, obviously, the decibel scale, you can see that it is a logarithmic comparison. And so when we use the normal scale, if we just report the amplitude ratio and we don't have a decibel scale, you'll notice that these gain axes will be logarithmic. But if we report that in decibels, they'll typically be linear. Like they'll appear linear in the decibel scale, but you just have to remember that decibels are a logarithmic transform. And so the graph will look the same, whether I'm using normal units on a logarithmic scale or decibel units on a linear scale. We will almost always report these things as having those decibel scales. So I'm trying to reproduce a signal of 22 kilohertz, which means that we have to filter out all of those frequency components below that frequency. We filter it out completely, and it is this kind of brick wall filter. We try to get close, and you can imagine that there's kind of an amazing array of different filters that have various success at approximating such a perfect filter. So these really, really perfect, like square lines, if you think about nature, doesn't really make straight lines. So it's really hard to build a good brick wall filter. And so what typically happens is we kind of trade it off, right? Like, so we trade off, which is typically why we're actually sampling at 22 instead of at 20, because we just add in a little bit of an error factor so that we still reproduce all those signals successfully. So we have our original signal. We filtered out the low or the high frequency components that would mess up our sampling. It's important to understand that this has to happen using analog hardware. Why? Because the whole point is, as soon as we sample, we lose the ability to we can't then filter out later after having sampled, because fundamentally the act of sampling causes this aliasing problem. And so these filters are called anti-aliasing filters. And they have to be hardware filters, okay? By the time we've then sampled it, we now have, and it's important here to understand what we have when we have a sampled signal. We don't anymore, it's like inappropriate to draw a smooth graph, because at that point, we only have values at times. And so most of you are pretty comfortable with kind of spreadsheet versions of these signals. And so we just look at what the signal value is at that moment in time, we write it down, and that's now the act of sampling. So that's how we record the information. And then, like, you can imagine that there's now a whole set of choices to make about how exactly that gets represented on physical media, but it's fine if you just imagine that, like, all the kind of analog processes you've ever done in your life, whenever you've looked at something that is changing continuously and taken the time to write down the value at particular moments in time, you have been doing sampling. So if you tell yourself, I'm going to write down the value of the temperature at every 5-minute intervals or whatever, you're doing sampling. And if you have a spreadsheet with those numbers in them, you have now a sampled signal.